So let's suppose we've got some constant signal, and let's say the constant is 1, just to keep it easy. And then we've got some additive noise on it, okay? So the signal is x of n equals 1 plus e of n, where e of n is drawn according to a normal distribution with mean 0 and variance sigma squared. So that's our process. So if we want to estimate, let's say we know it's a constant in the presence of noise, and so we know that we can estimate it by averaging. So we can say, let's call it mu hat sub x is by definition 1 over n. So we always have some finite data record. Let's say we have n samples here. So 1 over n times the sum from little n equals 0 to n minus 1 of x of n. So that's our mean. And I could have written that in terms of the expected value notation as expected value of x of n, which is the time average. And we only have these n samples, so that's where we're going to do our averaging. So suppose I get another sample of noise. Well, one thing to remind you is that recall that we derived that the variance of the estimator, mu hat, the variance of the sample mean. Now let me just mention that that's the sample mean. It's a mean derived from a sample of the random process. So the variance is essentially the standard deviation of the noise over n, the number of samples. So now, if we go to another block of capital N, we can divide that by 2n, right? So now let's look at the DFT. Let's consider capital X of 0, which is by definition just the sum of xn e to the j 0. We're only going to look at the DC component here. So you can see that that's equal to capital N times mu hat of n, all right? So the DFT is n times the mean. So in particular, the variance of x of 0 is equal to sigma squared over n times n, or sigma squared. So in other words, it does not go down. No matter how long our DFT is, it's going to have a variance that is proportional to the variance of the original process. So we're not really getting any average when we take the DFT, so we have to do some averaging. But now notice that, also notice that x0 is, well, let me expand it out a little bit. It's the DTFT at bin 0 of x, viewed as a vector. And that equals n times the mean, which is 1. I'm just writing it because I think it looks nice to say that, plus the sum of samples, n equals 0 to n minus 1. So that is now the signal that we have. And so what is the power of this? So if you take now the expected value of x of 0 squared, what do you get? You get n squared times mu sub x squared, I'll leave that in, plus the cross term 2n mu sub x, sum of 0, just go ahead and say it, it's going to be 0, plus n times sigma squared. So the thing you can say here is that as you get longer and longer FFTs, your your mean is getting multiplied by n squared, okay? So the mean times n squared, whereas this is just 0. The cross term is 0 because the noise is 0 mean, and the noise times any constant, such as n times the mean, is 0 mean. So that's just 0. And then here we have the variance times n. So you see that there is a benefit. So if you take longer and longer DFTs, you will see, so the mean becomes n, right? And then your noise, the FFT of noise is just noise, right? So it's just noise. And the variance is n times sigma squared. So that means that the standard deviation is down around square root of n. So I'm taking the square root of the variance and plotting just the DFT itself, the DFT of x of length n. So the sigma, let's call this sigma sub capital X, and so this is mu sub capital X at 0. I should probably put a 0 there. This is all k, all bends. So you see the point that every time you increase let's say you double the DFT length. If you double the DFT, if you double n, the DFT length, that means plus 6 dB for the mean. Let's say for the DC component, and plus 3 dB elsewhere. You see that? And this is precisely because the constant, every time you double the DFT, you double the amplitude of the DC component. So you're summing, you're finding the DC component as just the sum of samples, and if you double the number of samples, you've added 6 dB to that result. But the noise does not add coherently. The noise does not add on an amplitude basis. The noise adds on a power basis, so you only get a 3 dB increase in the noise. So it looks like your signal-to-noise ratio goes up as you take a longer and longer FFT, but that's just what we would call processing gain. So there's no fundamental change in signal-to-noise ratio. It's just the difference between a 6 dB per doubling and a 3 dB per doubling, whether or not it's deterministic or stochastic. All right, so that's why you can get any apparent signal-noise ratio you want by taking longer and longer DFTs. You can just keep enlarging the DFT until the deterministic signal comes out of the noise. And I actually happen to work in the area of underwater signal processing, and we were digging signals out of the noise that were minus 40 dB signal-to-noise ratio. So the signal is 40 dB below the noise level, but with enough averaging, if you can find it and average it, you'll eventually win, right? Because you average the deterministic stuff coherently, and the noise averages non-coherently, and for every doubling there's a 3 dB difference, and so that's your processing gain.
But then you lose time resolution.
Right, yeah, we're using up all the time we can. Right.
So I mean,